Okay, so what we did last time, we talked about the inductor, and we said that the inductor will have an impedance, and this impedance of the inductor is equal to j omega L. So basically, the inductor will be replaced in AC analysis with a j, imaginary number, and omega, which is the frequency that comes from the supply. The supply will dictate the this omega and the value of ZL, which is an impedance, and its value is in ohms. So we can add it to the resistance. Now today we'll do the same thing for the capacitor, and we'll start with the same thing. So we have a capacitor with C, has VC and IC. So let's assume that VC is equal to Vm sine omega t plus theta. And we know that IC is equal to C dVC by dt. This is the relation that we know from our previous discussion about the capacitor. So if this is the case, then your IC is equal to C Vm, and then the derivative of this, which is omega cosine omega t plus theta. And I mentioned you can start with cosine. It will not make a difference. So we can start VC with a cosine. It's the same thing, but the math here is easier. That's all. Now we can write down the VC and IC from the time domain representation into a frequency representation. Okay, so let's see this. So your VC will equal to a magnitude Vm angle of theta minus 90, because this is sine, so we convert this to a cosine. Same thing what we did with the inductor. And your IC will equal to omega c Vm angle of theta. Now again here we will define ZC, which is the impedance of the capacitor. So it's not the capacitance, which is unit is farad. Now this unit is in ohms. So it's equal to VC divided by IC using Ohm's law. So this is equal to, so when we divide, as we mentioned before, we want to keep everything in polar format. So this becomes Vm theta minus 90 divided by omega c Vm angle of theta. So the Vm will cancel. So this becomes 1 over omega c angle of minus 90. Now we can represent this in a different ways. So we can say that this is equal to minus j over omega c, because one angle of minus 90 is nothing but minus j. Same thing, one angle of 90 in the inductor, it is just a j. So if it is minus 90, it becomes minus j. Or sometimes we will say this, okay, this is 1 over omega c, and take this down to the denominator. So this becomes 90. So this becomes 1 over j omega c. So it's either 1 over j omega c or minus j over omega c. But we always prefer to have the j in the numerator. So even with this, we multiply by j over j. So this becomes j times 1 is j. J times j is minus 1 divided by omega c, which is back to this one. So this is more standard way, because we always want to keep the j in the numerator, not in the denominator. Okay, so this is the relation for the capacitor. So this is very interesting now. So now we have the inductor will be modeled as j times omega times L. And the capacitor now will be modeled as minus j over omega c. So both the inductor and the capacitor, both of them are having an imaginary number, j or minus j. It's not real, but both of them have a unit is ohm. So now your impedance become a complex number. That is the only thing that is different than what we used to do before. So VC, as I just mentioned, equal to Vm theta minus 90, IC equal to omega C Vm angle of theta. So if we use or make this is equal to theta instead of minus 90, then we have to add the 90 here, because there is a 90-degree phase shift between the current and the voltage. So when this is theta minus 90, this becomes theta. If I make this as theta, then this becomes omega C Vm theta plus 90. So this is has the VC has less angle by 90, or IC has more angle by 90. Both means exactly the same thing. And if I multiply omega C Vm, I will call this as Im. So we can put this now in the phasor diagram. So in the phasor diagram here, you will see that the current leads the voltage by 90 degree. In the inductor, the current lags the voltage by 90 degree. And this relationship is always the case. They are opposite to each other. The inductor and the capacitor, one is plus J, one minus J. So sort of they will cancel the effect of each other. And this is something very important in electrical engineering, uh, and this will lead to many important phenomena, but we don't talk about them in this course. We talk about them in more advanced course in electrical engineering. So in conclusion, the current through the capacitor leads the voltage by 90 degree. Now when it comes to the resistance, there is no phase. It is an R. It's a real number. So Ohm's law, either in AC or in DC, there is no difference. So R is the real part of your impedance. So ZR is equal to R, and because there is no angle, the current and the voltage, they are in phase. There is no phase shift between them. When you have the voltage and you have the current, there is no leading, there is no lagging, because R itself doesn't have any angle to influence. So when we have ZR, which is equal to here, or R, your V over I is equal to R. R here has no angle, zero angle. So this is why we see that the voltage and the current, they are exactly have the same zero crossing. But if you go here, you will see that the current leads the voltage. So the zero crossing here is ahead of. So the current will reach the zero before the voltage will reach the zero. So the current is leading the voltage, or the voltage lags the current, but we always use the current as our reference. So this is, in conclusion, what exactly we have, or our knowledge about R, L, and C in time domain and in frequency domain. Frequency domain, which we call it the phasors, same thing. So we call it sometimes frequency domain, and sometimes we call them phasors. So in time domain, Ohm's law, this is the relation between V and I. V equal to Ri. In frequency domain is exactly the same. There's no difference. So the resistance stays the same. Either you talk about time domain or frequency domain. Now for the L, V is equal to L di by dt. This is the relationship that governs the voltages and the current. And the voltage is equal to L di by dt. But in frequency domain, we use Ohm's law. Here it is V equal to, this is what we call ZL. So the impedance times I. Here R times I. Here it is ZL times I. When it comes to the capacitor, I equal to C dV by dt. Again, Ohm's law. V is equal to I times 1 over J omega C. Okay, so this is the I, and ZC is this. Your ZC is the 1 over J omega C, or minus J over omega C. Both means exactly the same thing. So this table is very important to summarize the relationship of the inductor capacitor resistance if you are working in time domain or in frequency domain. Now we don't work much in time domain. We don't want that. Why? Because this will lead to differential equations. and we don't want to solve the system of differential equation, we said that the advantage of working in the frequency domain, that I will convert everything from differential equation to algebraic equations. The only thing that I need to be aware of is that these equations are in complex numbers. That's all. There is nothing else that I need to worry about. Now, when you go to the extremes, now we said that z is equal to j omega l. Okay, so what would happen to z if we have frequency is zero or the frequency is infinity? Means very, very low or very, very, very high. So if this is very, very low in DC, omega equal to zero, z is equal to zero. It means it's the short circuit. So if you're working with a very little frequency or zero frequency, so Z can be treated as a short circuit. Now, when you work in a very high frequency, of course, there is nothing called infinity in reality, but if you go for very, very high frequency, so it is somehow, you can look to it as if it's infinity, then Z itself becomes infinity. So it becomes like an open circuit. So here, the inductor behaves at the two extreme point from short circuit and goes to open circuit during the charging process. Okay. Now, in between, it is like this. It is j omega L. The capacitor is the opposite. At omega equal to zero, this is when you divide by zero, this becomes infinity. Okay, so this becomes an open circuit. When omega goes to a very high value, so the capacitor becomes a short circuit. So the capacitor starts as an open circuit at a very, very low frequency and then evolve to a short circuit at very, very high frequency. Now, this phenomena, moving from short circuit to open circuit in the inductor, or open circuit to short circuit in the capacitor, this is the basis that we'll use in designing the filter. Later on, when we talk about the filters, that is the basic thing that we will be dealing with later on. Now, let's put everything into perspective. Let's assume I have something like this. I have a circuit, and this circuit, AC circuit. So here I have a magnitude of, let's say, a cosine omega t plus theta. So this omega t can be anything. And then I will have a resistance R, and I will have here C, capacitors, L, and I want to find I of t, the current in time domain. Okay, so the first thing you have to do, this is the steps, how to approach a circuit when it comes to the AC analysis, how we will solve the circuit. So first, replace the time descriptions of the voltage and current sources into phasors. So this, I will replace the A cosine omega t plus theta. I will replace this into an A angle of theta. Okay, so there is no time domain here. So this is the first thing. Every supply, you change it from time domain representation, which is a cosine or a sine. Remember, if it's a sine, then you add minus 90 to it and you convert it to cosine. So it has to be in cosine. Sometimes the question will be given to you as such. In this format. It will not be given to you in a different format. Then you don't need to do anything about it. If it's given in this format, in the phasor format, then you are okay. But if it's given in the time domain, I don't want to deal with differential equation. So I don't want to see anything in time domain. So this is what I need to do. Number two, I will replace every inductor by j omega L, every capacitor by 1 over j omega c, and every resistance I will keep it as it is. So if you go back to the previous example here, I will replace this with, instead of L, there is no L. It is j omega L, and this is in ohm, and this is minus j over omega c, or 1 over j omega c, but as eventually you will use this, and this is also in ohm. And R, of course, keep it as it is, and this is also in ohm. So now you converted everything in ohms. Okay, and now you are ready to start working. Then analyze the circuit using any of the techniques that we know. Okay, then you will work with nodal analysis, KCL, KVL, whatever, voltage division, current division, and we will have an example. Every single circuit analysis technique that we learn, we will have an example about that. Okay, once we are done, found our value in phasors, we convert them back to the time domain. Okay, so let's say I found I has a magnitude and an angle, then this I of t becomes equal to the magnitude cosine the same omega t plus phi. And then my problem is solved. If my interest is to find I of t, sometimes no, my interest is stopped here. Then I don't need. So it could be in polar or it could be in x plus j y, could be in rectangular form. Now let's have an example. And as I said, we will have multiple examples as we move on. Here we want to determine the input impedance of this circuit, giving that omega is equal to 10. So omega, you should know omega. You have to know omega. Either I will give you to explicit like this, or alternatively, I will give you the supply. And from the supply, you extract omega, and this will be your omega. So we want to find Z here. So it is exactly what we used to do before in the resistance, or finding the equivalent inductance or equivalent capacitance. You see things in parallel, in series, and then you add them, and then you find the total Z. But here, when we look here, we found that the capacitor is given in millifarad, the inductors in Henry in millifarad, and that's you should not do, and this is very important, please write it down here. You should not do the addition or parallel or series connection when the capacitors is in farad or the inductor is in Henry. Why? Because they are different units. You have to convert this into j omega L so that it will be in ohm. So if it is in ohm, you can add ohm with ohm, but you cannot add Henry with ohm. Same thing for the capacitor. You have to change it to minus j over omega c so that you will be able to do that. Okay, so let's move on here. Now let's do so the first thing. Now omega is equal to 10. Omega is equal to 10 given to us. Before doing anything, any circuit reduction, I have to convert everything here into the ohms or the impedance. So the 2 millifarad, this is equal to minus j over omega c, equal to minus j over omega is 10 and c2 times 10 to minus 3. So this becomes 10 to minus 2, 100 over 2. So this becomes minus J50. So there is no 2 millifarad anymore, and this is equal to minus J50. Now for the inductor, it's already given to you. It is J omega L, so it is J times 10 times 2, so it is equal to J20. You can see here, this is J20. Now let's see the 4 millifarad, so which is minus J over omega C minus J over 10 times 4 times 10 to minus 3. So this is equal to minus J25. So there is no 4 here, and this is minus J25. Now, after converting every inductor, every capacitor to the values I'm looking for, now I am set, I am ready to do what? To do the addition, subtraction, parallel series, everything in my circuit. Now, first thing, this is exactly the same approach we will do when we find that equivalent impedance. When you look here, these two are in series. So I will call this Z 1. So your Z1 is equal to 50 plus J20. And now here, very important. This is imaginary number. This is real number. They don't mix. You add them, but you keep everyone separate. So this represent the real part. This represent the imaginary part. Now we'll go to from here to Z2, and you clearly you can see that this capacitor is in parallel with this branch. So the two nodes of the capacitor here and there, and the two nodes of this branch, which is Z1, is between the same two nodes. So they are connected in parallel. So I will call this is Z2, which is say this is minus J25 in parallel with 50 plus J20. Now, one thing we learn when we have things in parallel, we multiply them and divide by their summation. So this is equal to 50 plus J20 times minus J25 divided by 50 plus J20 minus J25. Now you do the multiplication. So multiply this with this minus J1250. Multiply this with this. So J times J is minus 1, and there is a minus 1. So this becomes plus, and 20 times 25 is 500 divided by 50. There's no real part, so it stays as it is. And then we will have here J20 minus J25. So this is minus J5. Now that's not sufficient. Why? Because now still we don't have one full number. I have to put it in the form of A plus JX, or A angle of theta. Okay, so I have to do the division. Now with the division, we said it's better to do it in the polar format. So still we are not done. So I have to convert this into a polar number and this into a polar number. And we can do this using the what we used to do before. Now, one thing we can do here, we can simplify this little bit. I can take 5 as a common factor here. So this is 5. We can do a bit of so this becomes 100 minus J 250 divided by 5. This becomes 10 minus J. So this will cancel with this. So this is a little bit of manipulation of the numbers, just trying to reduce the numbers, dealing with the better numbers here. So now this becomes, now using the calculator, I will convert this. So this becomes 269.26, and the angle is 291.8 divided by 10.05, angle of 354.29. Now, how many decimals you have to use? Well, I would say 1 is sufficient. Or 2 at maximum. If you want to do put more, don't exceed 2. That is the maximum you should put. But 1, I would say, is sufficient. So now we divide the real with the real number. So this becomes 26.79, and then you subtract the numbers. So this is equal to minus 62.49, 291.8 minus 354.29. So when you subtract them, you get this number. Now, what we have now, everything here, the inductor, the resistance who were in series with the capacitors in parallel, has this value. Now, everything here, which is Z2 now, is in series with this branch. So now everything which is Zn, which we want to calculate, is equal to the 20 ohm, this 20 ohm, and in series with this minus J50, plus in series with this, which is 26.79, angle of minus 62.49. So now I am adding a rectangular number into a polar number. This is rectangular, and this is polar, and this is not possible. So what we need to do, we need to convert this into rectangular back. So this is equal to 20 minus j 50, and then plus. So we will convert this. This is equal to 12.37 minus 23.76. Now we add the real to the real. So this is equal to 32. Now, as you can see here, the math, it's mainly the math here. It's straightforward, but the math is the thing that is slowing us, and that's why you need to understand the math very well. Now the imaginary with the imaginary, so this is minus j 73.76. So it's very important to master working with this. And I said you guys are a bit lucky because you are working online, and online you will just need to deal with the calculator. That's all you need to do. Okay, now let's start to have more interesting questions, more demanding questions. So let's see this one. So here we want to find I of t. Okay, I want to find I know this is a circuit question. Okay, now we need to do exactly what we used to do: convert the sources, convert the resistances, and then find whatever in I as a phasor, then convert it back into time domain representation. So here we need to convert this. The source has to be converted. The capacitor has to be converted. The only thing that stays as it is this 20 ohm. Nothing will happen to it, and the inductor need to be converted. Okay, so once we convert everything, then we will be able to solve this question. So let me just make it neater. Okay. Okay. Now let's do that. So this is what I want to find. I mean, as a convention, sometimes we use capital letter for the phasors and the small letter for the time domain. Now the source is 120 sine 377t plus 60. So I need to subtract 90 to convert it to a cosine. So this becomes 120 cosine 377t plus 60 minus 90. So this is equal to 120 cosine 377t minus 30. So now my supply is here 120 angle of minus 30. This is my supply. So forget about anything else. Okay, now what is omega? Because I need to change the capacitor and the inductor, so I need to find omega. What is omega? Can someone tell me here what is omega, guys? What is omega? Excellent, excellent, Alexa. It's 377. Thank you, guys. Very good. So I just make sure that you guys are awake, not yet sleepy. So omega is equal to 377 radian per second. Okay, now this is very important because without the omega I cannot proceed. Now I have to convert the inductor and the capacitor. So I want to find ZL, which is equal to J omega L, which is equal to J. What is omega? 377 times L 40. But remember, this is in millihenry, and this has to be henry here. So I have multiplied 10 to minus 3. So this will give me J 15.08 ohm. So this is J 15.008. We are left with the capacitor, which is ZC, which is equal to minus J over omega C. So it's equal to minus J over omega, which is 377. And C is equal to 50 times 10 to minus 6. Okay, and if you do the calculation, this is equal to minus J 53.05. So this is minus J 53.05. Again, ohm. Now I want to find I. Now it is up to you. What do you want to find? How do you want to find it? You can use any technique. You can use nodal. You can use anything. So the one that I did, I found Z equivalent, and then I, using Ohm's law, is equal to the voltage divided by Z equivalent. So I'm converting this into simply like this, the supply, which is 120 angle of minus 30, and we have here Z equivalent, which is this and this in series in parallel with this. Then your I is equal to the 120 angle of minus 30 divided by Z equivalent. So all I need to find now is Z equivalent. What is Z equivalent? As I said, your Z equivalent is equal to this plus this in parallel. So your Z equivalent okay, sorry about that. Z equivalent is equal to 20 plus J 15.08. This is in parallel with minus J 53.005. And when you do the calculations, I don't need to go through this. Now you add this, and then multiply it by this, divide by this summation, and you have all the interesting stuff with the math. So please do this. And if I do this, this will be equal to 30.56 plus J 4.97 ohm. So from this, your I is equal to this 120 angle of minus 30 divided by this. Now, because I'm dividing, I know that I have to convert this into polar. Okay, so if I convert this into polar, so this becomes 30.96 angle of 9.224. Now with this, your I will equal to, we divide the real numbers together, so this equal to 3.870, and the angle will be equal to minus 39.224. Okay, then once we are done with this, your I of t is equal to magnitude 3.87 cosine omega t, which is 377t, and minus 39.24, which is your angle here. Okay, so this is as simple as that. This is the value of your I of t. Okay, so what is left here is just, I have one bonus question for you guys. Okay, and the fastest one will give me the answer, of course. This is a very straightforward, very simple circuit. Okay, but the fastest one will give me the right answer. He or she will get the bonus mark today. So get ready, guys. So we have here a supply, and our supply is 100 cosine for t. We have 1 ohm resistance. We have here 1/4 farad, and what we want to find is this voltage. I want this into time domain. What is V of t equal to what? Go ahead, guys. So it is a resistance in series with a capacitor in series with this voltage source, which is equal to 100 cosine 40. So it's very simple question, but this is for you to start get engaged with AC analysis. Go ahead, guys. So give me the V of t. I need the voltage in time domain. So here you need to do everything. Convert the voltage source into a phasor, and then convert, I mean, R stays as it is. The capacitor is minus J over omega C. Find V as a phasor, then convert it back to V of t. You can use any technique here. You can use KVL. You can use voltage division. You can use any technique you feel comfortable. You can use nodal. But there are a couple of good techniques that can be used. This is also for you to appreciate the effort in the AC question. I mean, the AC question is not, I mean, the circuit, if we have this in DC, it will be just one line. That's it. But in AC analysis, there is first a pre-processing, and then there is the analysis, and then the conversion back. Of course, you will never get a circuit like this in the exam. Okay, it will be much more complicated than this. Okay, so I mean, I want you to have the feeling that in AC analysis, we need to be worried about the time, and you need to be quick in doing the analysis because there's a lot of things need to be you need to take care of. I will pause the recording. So let's now, okay, let's resume the record. Now let's solve the question. So we'll have a winner here. Emma, please send me an email to get your 0.5 bonus mark. Okay, so now let's apply what we have learned here. Okay, so the first thing, we need to convert the circuit. So the circuit has to be converted. So we need to convert the supply, and we can convert the capacitor. Okay, so the supply is 100, and the angle is 0 because there's no phase shift. So angle is 0. This stays as it is, and this is minus J over omega C. So minus J, omega is 4, and C is 1 over 4. So this is equal to minus C. So I gave a simple question in math so that you can get it right. Now I will use voltage division. So this voltage across the capacitor V is equal to the main supply, which is 100 angle of 0, times this impedance, which is minus J, divided by the summation of the two impedances in series, which is the voltage division, 1 minus J. So I'm multiplying a polar number times a rectangular. I have to convert these two into polar. So this is 100 angle of 0 times this is equal to 1 angle of minus 90 divided by root 2 angle of minus 45. So we'll divide the magnitude, which is 100 divided by root 2, and the angles, will subtract them. So it is 0, or add them. Here we add 0 minus 90, and then subtract it from the 45, minus 45. So this is equal to 70.7 angle of minus 45. So this is your V as a phasor. So your V of t will equal to 70.7 cosine or reference times omega t. Omega, will get it from here. It is 4t and the phase shift minus 40, 45. So this is how we'll deal the question. So next week, we will start to build the momentum. We'll start to have a harder and harder question until we reach to the exam level. Okay, guys? Okay, I'll stop the recording now.